Before we go into details of measurement, first of all, a little bit physical fundamentals to start really from scratch. So we have natural fields around us. So we did not invent the fields. They were already there around us before people began their cycle on the Earth. So we have, for example, the magnetic field, which every sailor knows. By the compass, he can get an orientation, and then he knows where north is by the magnetic field, which is around our world. And also we have an electric field, not only the magnetic field, but we also have an electric field, which can have some 100 volts per meter at good weather. And in thunderstorms, you can have some kilovolts per meter. And sometimes you can even see the effects by flashes, for example. So these are natural fields, but on the other side, we have tons of man-made fields. And as they are not natural, we are a little bit worried about them. So we have the power supply of a train, a simple hairdryer producing a strong magnetic field, power supply, broadcasting, we have radar signals around airports and so on. So we have a lot of man-made fields. And we also have our rules, how to measure their field strength. Not everything is allowed. How do we create an electric field? So the most simple way is we take a battery of 1.5 volts, we connect it with two metal plates, which have a distance of 1 meter, for example, and then we have an electric field of 1.5 volts per meter between the two metal plates. Okay. If we connect, for example, a light between the two wires, then also a current is flowing. And if there is a current flowing, we have a magnetic field around the wire. The magnetic field is also created directly by the current, and we can also calculate how high is a current depending on the how high is the magnetic field depending on the current through the wire. Okay. And if we are talking, those were all static fields, but if we are changing the polarization of the battery, we can also change the polarization of our electric field. If we turn it around by 180 degrees, the polarization of the electric field is changing from upside down to down, upside, I don't know. And if you turn the battery around by 360 degrees, you can have one complete cycle. And if you do this within a second, we have a frequency of the field of around about 1 hertz. If we do it, for example, 1,000 times, we have 1 kilohertz. If we do it 1 million times per second, we have 1 megahertz. If we do it 1 billion times, we have a gigahertz. So by this, we can create alternating fields, which are mostly used in telecommunication, for example. When we talk about telecommunications, where do we find our different applications? Here we have on the x-axis a frequency range, and you can see here on the left-hand side we have the static field. The frequency is 0 hertz. And here we have, for example, our static magnetic field around the Earth. At 50 or in the US, or we have our 60 field power supply, the AC frequency at 50 or 60 hertz. Then we go into the intermediate frequencies, some 100 kilohertz, some megahertz. Here at 100 megahertz, we have our FM radio, for example. At 2.45 gigahertz, we have microwave ovens. At 33 gigahertz, we can have digital radio links. And our definition of electromagnetic fields, where we are discussing about, is the limit 300 gigahertz. This is finally the end of all legislation we have for EMF, because above 300 gigahertz, the infrared light is starting, and they have different rules and legislation. Okay. So you can also see sometimes we say frequency in hertz, kilohertz, megahertz, and sometimes we talk about wavelengths, 100,000 kilometers, 100 kilometers. The relationship between both is given by a rule we will see a little bit later. Let's have a look a little bit about 300 gigahertz. Maybe you know your mobile telephone stops at around about 6 or 7 gigahertz, not more. But in 5G, we are talking now about the frequency range 2, which is in some countries already installed. And these are frequency around 40 and 30 and 40 gigahertz. And 5G wants to go up to 70 gigahertz. So we are getting closer and closer to the 300 gigahertz. Above 300 gigahertz, we first of all have the infrared light, then we have the visible light, and then we go into the ultraviolet light. And here in the ultraviolet light, we also have the barrier between the so-called non-ionizing radiation and ionizing radiation. Ionizing radiation is much more powerful than non-ionizing radiation. And ionizing radiation, we also talk about the X-rays and so on. So here we know exactly what dose produces cancer inside of our body because it's damaging our cells. Non-ionizing radiation is normally not strong enough to produce such kind of effects. Okay, so non-ionizing radiation is the safer area, let's say, but still we can also have here biological effects which are proven, and we will see them a little bit later. Non-ionizing radiation on the left-hand side, ionizing radiation on the right-hand side. I told you about wavelengths and field strengths, wavelengths and frequency, sorry. The relation between both is given by the speed of light. The speed of light is 300,000 kilometers per second. So it's not infinite, it's just 300,000 kilometers per second. So the distance to the moon within a second. And if you divide this by the frequencies, you get the wavelengths. And one figure I always know, this is 100 megahertz. FM radio is a wavelength of 3 meters. And from there, you can now calculate 300 megahertz means 3 times the frequency means a third of the wavelength is round about 1 meter. Okay, you just have to know one value. From there, you can calculate 1 gigahertz means 0.3 meters wavelength. Easy. Here are some applications and their frequency and wavelengths. So when we talk about mobile phone at 900 megahertz, we talk about a wavelength of 0.33 meters, 33 centimeters. FM radio, I just mentioned it. Power supply, for example, at 50 hertz, the wavelength is 6,000 kilometers. So sometimes the wavelength is just more impressive to see the values, and why we will see a little bit later. So when we go closer to an antenna, and if we go close to the antenna, we will see that very close to the antenna, the magnetic we have a magnetic field and we have an electric field. Magnetic field, the H field, and electric field, the E field. You can see that the electric field has here and the, so this is a simulation of an FM transmitting antenna. You can see here 4 transmitting elements. And when we go to one of those, the upper element here, for example, you can see in the center, we have a hotspot of electric field. And we go to the magnetic field, at the center, it has a null. So there is nothing nearly transmitted. The H field has at the top and at the bottom of the element, it has its hotspot, via the electric field is there very little. Okay, so close to the antenna, electric field and magnetic field are completely independent from each other. So close to the antenna, we have to measure both electric field and magnetic field. You can compare it with the waves of a boat which is driving through the sea. Close to the propeller, you can't see a clear wave structure. If you look some meters away from the boat, then you can see a clear wave structure. The world is okay. The same happens also to our antennas. When we go a distance away from the antenna, then the electric field and the magnetic field are no longer independent from each other, but they depend on each other. They are perpendicular to each other. And then it's enough to measure one of the components and you will be able to calculate to the other components. So you measure, for example, the electric field, and you can calculate the magnetic field. Close to the antenna, this is not possible. Okay, so now the next question which pops up is where is close and where is far? So there we have a very rough rule, which means 3 times the wavelength means if we are closer than 3 times the wavelengths, we are in the near field. Near field, electric field, H field are not in phase. We have to measure both. More than 3 times the wavelengths, we are in the far field, and then electric field and H field are in phase. Just one measurement is enough. So remember, FM radio wavelength was 3 meters, 100 megahertz. So then round about 3 times the wavelength means 9 meters away from an FM tower, you are in the far field, and there it is enough to measure one component. This is a rough rule of thumb. There is no 100% barrier that at 2.99 we are in the near field, and 3.01 we are in the far field. So there is a sliding barrier between both, and there are also other definitions, and also this rule is not guilty for everything. So for example, when we look to radar antennas where the wavelength is very short but the diameter of the antenna can be very large, there we have different formulas. But for normal transmission of broadcasters, maybe also mobile radios, we can take this as a rule of thumb. Okay, 3 times wavelength. Remember, wavelength of power supply, 50 hertz, was 6,000 kilometers. 6,000 kilometers multiplied by 3 is 18,000 kilometers. So for power supply, we are always in the near field. Okay, far field is 18,000 kilometers away. So we are always in the near field. Electric field and magnetic field are always independent from each other. But with broadcasting, it's changing. Okay. So another example is microwave oven 2.45 gigahertz means a wavelength of 12 centimeters. So from 36 centimeters away from the microwave oven, you are in the far field. One measurement is enough. And normally you measure the electric field because electric field probes have a much broader frequency range compared to magnetic field probes.